Yonsei University の方が好き、今に狙いましょう。
Yeah.
The G-saying that since the Yonsei University non-local scheme has to define the whole of the area by some dynamical structure, it might be condenser water.
That's a good question. It's possible. At this stage, I have not looked. The Yonsei University scheme it uses a first order closure above the boundary line top with a smallish mixing length, but it would still produce a reasonable amount of mixing above the top, so that may help. The other thing that scheme has is it has a entrainment parameterisation at the top, and it has a counter-gradient flux parameterisation at the top, both of which would provide it with some additional mixing if the height was too slow, if the diagnosed height was too small. Nevertheless, there's a paper just out in the Quarterly Journal, which I mentioned to someone, I can't remember whether it was you or not, but they were comparing the simulations in 4 different storms and in 4 different PBL schemes, and they were finding that the Yonsei University scheme was producing relatively quite a small amount of parameterised mixing, which possibly is consistent with the diagnosed top being too small.
For the intra-boundary layer of the because it has a separate total mixing X and intra-boundary layer.
Yeah. So it would be easy to check, and it would be a matter of getting hold of a WRF simulation and looking at the depth of the boundary layer and looking at the diagnosed height, which is probably available as an output from the model.
JMHM also has a non-local type scheme.
Sorry,
JMHM has also the non-local type scheme, and I compare the result of the
Okay.
It first determines the height of the PBL by theta W, and there are some additional layer above the total.
Yes.
But
Yes, the unified model that we use also uses a non-local closure under. It uses a first order closure under unstable conditions and a non-local closure under stable conditions, which makes it quite a complicated scheme. We've had a quick look at the tropical cyclone boundary layer in that, and it looks to be quite good, but of course it's probably it's based on the stability at the surface, which in the SE temperature difference essentially. So it would be running in the first order closure mode probably most of the time. But it's I think it's a bit of a warning that these the one-dimensional thinking and the constant theta, these are I guess standard ways that people think about the boundary layer, and the tropical cyclone boundary layer is actually quite different. So there is a need to go back to the schemes and to verify that they're actually doing something, something reasonably sensible.
I heard the Xu Chen's group consider the ocean cooling around the Iowa regions, it stabilizes almost the surface layers. So, but your calculation doesn't include such kind of ocean feedback. So
I haven't got ocean feedbacks in.
So maybe I still think the ocean cooling can be a candidate to explain the stabilize.
Yes, but if it was ocean cooling, you wouldn't expect to see the superadiabatic layer near the surface. If it was ocean cooling, you'd expect to see stability right down to the surface.
Right.
But it's a good point. There are some additional computations we need to look at, and probably the effect of sea surface cooling isn't one of them. The other one we haven't included in this computation is there's a parameterisation of dissipative heating available in CM1. We have run the model with that switched on and it produces very similar structure, but we haven't yet analysed the results. Now the dissipative heating produces a warming right near the very surface, and so that could also be contributing to the surface sea path. So, work in progress. We hope to have a paper out sometime early next year and have answered all the, done a bit more work and answered all the residual questions. So in this next chapter, which is also a little short, we'll look at air-sea fluxes and turbulence. And I'm going to start by way of motivation, just to remind us about potential intensity theory. I'm sure that almost everyone here has seen it, but let's just go over this old ground first. So the question that potential intensity theory aims to answer is, given the environment, how intense can a tropical cyclone get? And it's a question that goes back a long way, at least to the 1960s. And probably the most, well, certainly the most influential attempt at answering that question has been in the series of papers by Kerry Emanuel and various co-workers at various times. It's a very important question. Applications include forecasting. There are intensity forecast techniques where a strong predictor of intensity change is the difference between current intensity and potential intensity. It's used for structure design and risk analysis. I occasionally get rung up by people in the engineering community who who want to know what's the worst possible cyclone we can get at this location because we need to consider our building codes. I'm currently working with someone who's doing a storm surge risk study for the Queensland coast, and she's been wanting to know what the quite fine scale potential intensity data through the year for the Queensland coast, because that determines how strong a cyclone she puts into the storm surge model and how strong they have to build coastal infrastructure. It's obviously important for theory because it's underpinned a number of, quite a bit of our theory, I understand, in the last 20 years. And it's been widely used for climate change studies because the question of what are the worst cyclones we can get in a warming world, it's a suitable tool for answering that question. So Kerry's theory consists of two parts. The cyclone consists of two parts, the boundary layer and everything else. Above the boundary layer, saturated moist descent is assumed to be neutrally buoyant. The flow, and that implies that the surfaces of saturated theta E and angular momentum coincide, and the flow is assumed to be in gradient and hydrostatic balance. Within the boundary layer, he uses a linearised slab model with surface friction and enthalpy flux via bulk formulae, and it's essentially the same formula that's in Uyama's famous 1969 paper. And later versions have dissipative heating in as well, which makes some difference to the results, which we won't bother about today. And if you take those assumptions and do a great deal of algebra, who's worked through the algebra in Kerry's papers? Anybody? Has anyone gone through the derivation of PI and sorted it all out? It's not easy, is it? You sort of work away and Kerry says, and now we get to this line, and you scratch your head and look at it for half a day and then you work out what he's done. After much algebra, you come up with much algebra. You come up with this formula, or a slightly different formula if you've got dissipative heating in. And this is the maximum wind speed squared, heat capacity of air, the surface temperature, the outflow temperature, enthalpy and drag exchange coefficients, and this is the saturated theta E at the sea surface, and this is theta E at the sea surface of the maximum wind. So this is basically the air-sea thermodynamic disequilibrium. And you know, that's the formula, and people have compared that formula to observed tropical cyclones, and it works reasonably well. And starting with Kerry in 1986, and subsequently probably hundreds, if not thousands, of other people have fed data from one model or reanalysis or something through the formula, and they've produced maps like this, which show you the intensity. This one is in terms of central pressure for various basins at various times of the year. So it's been very useful. The problem, or the challenge that came about when people started looking at PI theory, is that we really don't know how the transfer coefficients behave at high wind speed. And what we've always done in our models is we take measurements of those that are valid at low to moderate wind speeds, and we extrapolate. And at the time Kerry did this work, we had decent measurements of the drag coefficient up to a little over 20 metres a second, and the enthalpy coefficient up to somewhere around 15 or 16 metres a second. And so and this is a rough sketch map of what they looked like, but if you chop that map off there, that was about what we knew. The enthalpy transfer coefficient was about constant. The drag coefficient was fairly constant at low winds and then increased linearly with wind speed. And of course you extrapolate those off indefinitely and plug them into your model. What they found was that CK over CD, the ratio was becoming quite small at high wind speeds, and so the model was not predicting intense enough cyclones. So to get realistic results, you require CK on CD to be, there's different figures quoted, but definitely more than half, well over a half, perhaps 3/4 or more. Whereas the data at the time suggested that CK on CD became quite small at high wind speeds. So there were two methods proposed to fix that. Perhaps CK starts to increase at high wind speeds, and there was a lot of research done in the 1990s on sea spray fluxes. I was involved in that myself. The conclusion at the end of that was that sea spray was very interesting stuff, and that there were lots of curious things happening in the dynamics, but that it probably was not sufficient to explain the enthalpy coefficient going up. And the reason basically is that when a sea spray droplet evaporates, it's a wet bulb process. So it gives up some additional moisture, but it absorbs heat. And the overall effect on the theta efflux is very small. It's not quite zero, but it's very small. Or perhaps is the drag coefficient capped, this dotted line. There was some fairly weak evidence around at the time that it might be. There was one budget study by Bill Frank in 1984, and depending on it's quite an interesting paper to read if you make, as Bill says in it, that if you make one set of assumptions, then the drag coefficient goes up forever. If you make a different set of assumptions, then you have to get a cap on it. And that, and he sort of finishes up the paper by saying we really don't know which assumptions to use. It's quite difficult to get good drag coefficients out of the budget calculation. And there was a suggestion with storm surge models that if you used an uncapped drag coefficient, you tended to get a storm surge that was way too large, and so people were, in the storm surge modelling community, were putting a fairly arbitrary cap on to get their surge calculations to agree with the observations. But again, surge models have got lots of parameterisations in, and who's to say that it was really the drag coefficient that was the problem. So into all of this, a couple of things happened. This was, this conundrum with the PI was one of the things that drove the sea blast experiment. But slightly before the sea blast experiment, Mark Powell took some dropsonde data and produced a paper that appeared in Nature. Mark actually got his photograph on the cover of Nature, which is about as big as an honour as you can get in meteorology with this work. So in the surface layer, we expect to see a logarithmic profile, and U star is the friction velocity, square root of the stress over divided by the density, and Z naught is the surface roughness length. And Mark, figure 1 from Mark's paper pointed out that if you plotted the normalised wind speed from all eyeball dropsondes, you actually got something that was very close to a logarithmic profile. And so Mark said, well, if I take this data and stratify it by wind speed and fit this function to it, then I can estimate the roughness length. So his method was to fit curves to the observations. He binned them into various wind speed ranges. By fitting the curve, just by linear regression, you get U star and Z naught, and you can then get the drag coefficient from either of these formulae. They give you the same answer. Normally, if you were doing this method, it's called the profile method, you'd also have to calculate a stability correction, but Mark argued correctly that that was not necessary because the wind shear is so strong that the flow is close to being neutral. So it's people who've done boundary layer experiments. When I was at university, we went off on a field program once. We all camped beside a lake, cooked over a campfire, drank lots of beer, and we did some turbulence flux measurements. And we did them by a couple of methods, and one was the profile method, and we had a mast that was about that high with 6 anemometers on it, spaced right now. And with those anemometers spaced very close to the surface, it was actually, you could get decent measurements of the stress provided you were under neutral conditions, but the moment the sun came out and made it unstable, or at night when it was stable, even over such a small height range, it was quite a difficult measurement to do. And of course, Mark here is going up to heights of 200 metres and extrapolating down to heights of the order of a millimetre. And pretty obviously, you don't need to have much of a wriggle up here to make a huge difference in the Z0 that you get out at the end of it. So a lot of the, the people in the boundary layer community were very suspicious of these measurements and said, well, you really can't be doing that over such a large range because the method is so sensitive to small errors. But nevertheless, Mark's results showed something very interesting, and this is also from his paper. And so here is, these are all plotted against the wind speed. So you have U star. The symbols are Mark's results from, and they're over 4 different height ranges. I think he started from either 10 or 20 metres and went up to either 100 or 200. So the stress basically levels off beyond about 30 metres a second, and the roughness length increases and then comes down again. The drag coefficient increases and then comes down again. This line, the other lines are various other standard parameterisations. Mark's results tend to be a little bit on the low side of what was taken as standard, at say these 20 to 30 metre a second ranges, but certainly none of the standard parameterisations showed this decline of the roughness length or the drag coefficient. So it was a surprising result. Not only the drag coefficient was not just capped, it actually went down. So Mark's paper came out in 2003, and then there were a bunch of papers that followed in very quick succession. This is from a paper by Mark Donnellan, who at the time was at the University of Miami. Mark Powell, if you know Miami at all, the Rickenbacker Causeway goes from the city of Miami out to Key Biscayne. And if you drive out towards Key Biscayne, on your left, just before you cross the bridge, you see Hurricane Research Division, and on your right, you see the University of Miami. So the mark on the left of the road, published in 2003, the mark on the right of the road, published in 2004. So Mark Donnellan, who's a well-known Canadian oceanographer, at the University of Miami, he set himself up a very nice laboratory system, which was a wind tunnel. The working section of the wind tunnel was about 1 metre square, but the bottom half of the wind tunnel was full of water. And he had a wave generator at one end of the wind tunnel. He had a very good set of instrumentation in the wind tunnel for measuring the turbulence and particle motion, and he could run various wind speeds, and he could also change the frequency of the height of the waves that he was generating. I was fortunate to see the thing in operation, and it's really a great way to learn a bit about air-sea interaction, because you have the window, you can watch the waves go past and see them break and the bubbles form and get mixed in and spray droplets blow off the top. It's a tremendous facility. So Mark was using his wind wave tunnel, and he measured the drag coefficient plotted up here against the equivalent 10 metre wind speed. Of course, he hasn't got a true 10 metre wind in the wind tunnel. He has about a 30 centimetre wind, but he extrapolates up to 10 metres. And he got quite consistent results, linear increase up to about 30 metres a second, consistent with all that had been known before. And then at 30 metres a second, it basically levelled off. Didn't decline, as Mark Powell's results did, but it levelled off at about 2.3 by 10 to the -3. Mark used 3 different methods of calculating the drag coefficient from his wind tunnel data, which are listed up here. There was a profile method, the momentum budget, So Reynolds stresses, he basically did high frequency turbulence measurements. The profile method was the same as Mark Powell had used. The momentum budget, because you have a stress on the water surface, it actually requires a slight slope, and you can use that slope to calculate what the stress has to be. Extremely consistent results from all of them, and Mark Donnellan was also very well known in the boundary layer community, and so this really was regarded as a very strong confirmation of Mark Powell's results. So then along came Sea Blast. Sea Blast, they took aircraft measurements at a range of heights. Those measurements were then adjusted to give the equivalent surface flux. And the grey cloud is a whole bunch of previous measurements. The crosses were from the Hexos experiment, which was quite a famous experiment conducted in the 1990s in the North Sea to measure the enthalpy flux. It got up to about 18 metres a second, and the triangles are the Sea Blast results. And there's really, and up to 30 metres a second, there's really no evidence that the enthalpy flux is increasing. Obviously, there is a lot of scatter. That scatter is actually inherent in flux measurements because you're basically trying to measure a correlation. And you know when you measure a second moment that the sampling error in your measurement depends on the 1 on the square root of the sample size. So you actually need a very large sample size to get your sampling error down. And flux measurements typically have this sort of plus or minus 50% sampling uncertainty between one run and the next. And you really have to average a great many runs together to get a solid line. This is not evidence of or experimental technique or anything. It's inherent to doing any correlation measurements. And Sea Blast also had drag coefficients, and this plot, which is from there were 2 papers describing this in 2007 and JAS. So large at the pond was one of the extrapolated things that went up linearly. We have Powell's measurements coming down slightly, Donnellan's measurements here, and the Sea Blast measurements are perhaps a little bit more, have gone constant with wind speed at a slightly lower wind speed than Powell or Donnellan had, but nevertheless Sea Blast within the range of wind speeds is confirming that the drag coefficient is capped. So there was, at this point, there was growing observational evidence, and so people started asking my favourite question, which is the why question. And it's actually, to my mind, this was a fascinating episode in the history of the science. People had been talking about the possibility of the drag coefficient being capped for more than 20 years, and there had been almost no theoretical papers justifying a reason for it to be capped. In the 2006, in the 3 years after Mark Powell's paper came out, there were at least 1, 2, 3, 4, 5, 6 papers that gave theoretical explanations for why we had a cap on the drag coefficient. This is the same Mark Donnellan's wind tunnel experiments. He also had measurements of the airflow, and he explained the cap because at the very high winds, the air was actually separating from the waves. So rather than following the waves, there was a separation bubble behind the waves, which meant that as far as the atmosphere was concerned, it saw a relatively smooth surface. In my view, that is the most convincing explanation. There were papers that had other mechanisms based on the wave structure. And then Ed Andreas published a paper which he did a calculation in which he allowed for the momentum transfer by sea spray. So sea spray is generated when the wind whips the top off the waves. Those spray droplets accelerate to the wind speed and then they fall back in the ocean and they carry some stress as they do it.
In that sense, you know, just a comment, but sea spray stress enhances the drag coefficient rather than capping.
Yes, and Ed actually said that in his paper and said that he didn't think his mechanism was an explanation for Powell's results. I should add that Ed is one of the few people who still don't believe Mark Powell's results. So, and there was a paper by Vladimir Makin who argued that if you have a lot of sea spray in the atmosphere, then that creates a density stratification which is going to damp the turbulence, and that's going to have an effect on the fluxes. So these are all quite different explanations, and my impression is that there's still no consensus on which one is correct. As I said, I think Donnellan is the most convincing. One of the problems with Donnellan is that it's wind tunnel, and it's quite hard to get a wind wave tunnel to scale up to the real atmosphere correctly. So just to continue with the theme of the surface fluxes, I don't know if you've seen, some of you might have seen these photos. They were in Weather and Forecasting by Ed Black and co in the late 80s. There's also a NOAA technical report which has about 80 pages worth of these photos, which if you can find a copy of, it's very hard to get hold of, is a fascinating picture book. So this is what the sea surface looks like with a 20-metre wind of about 15 metres a second. So this is about gale force. These photos were all taken by a downwards looking camera in the Navy reconnaissance aircraft. So they're all quite close to the surface. This is, I put the captions on because it says this is 250 metres up. And the reason this work was done and the 80-page book of photos was developed was that back in the 1980s, the aircraft reconnaissance crews didn't have any remote sensing measurements for measuring the surface wind speed. In fact, they didn't have very good measurements for measuring the wind speed at flight level. And so the way they estimated the intensity of the hurricane was they basically looked out the window and then they flicked through the book till they found a photo that looked like what they were seeing, and then they read the wind speed off of that. So the moral of that story is be very careful about tropical cyclone wind speed estimates from the 1980s and before. So that's 15 metres a second. By 27 metres a second, we're starting to see the white caps are really quite extensive and large, curved shape, and we're starting to see these very prominent streaks aligned with the wind speed. So they are streaks of wind-blown sea spray. By 38 metres a second, so you know, this is a moderately intense hurricane. The white caps, and this is still very close to the surface, this is 285 metres altitude, so the field of view in all of these is quite similar. It's quite impressive how little white capping there is if you compare it to the previous one. Oops, wrong way. If you compare it to the previous one, there's a distinct decrease in the white capping, but a distinct increase in these ribbons of sea spray. And you can see there's quite a lot of structure which is presumably turbulence within those ribbons. And if we go to the, this is the highest wind speed that they had, the 50 metres a second. This is not a fault with the camera or anything. You're looking at enormous quantities of sea spray. So that's a 35% jump in wind speed. Perhaps these are white caps underneath. It's a bit hard to tell. There's still the streaky structure, but there's this enormous wash of spray.
Excuse me. Which direction is the wind direction?
I was afraid someone was going to ask me that. I think in this case it's blowing from bottom to top. It may say so in the paper. The amount of spray you get in the column, the rate at which spray is produced probably goes with wind speed cubed, and the depth of the spray layer probably scales with wind speed, and the residence time probably scales with wind speed to probably with a wind speed to some power higher than 1. So the extinction coefficient looking down probably goes as something like wind speed to the 5th, perhaps more. So it's not, in that sense, it's not surprising that we get this very, very dramatic change to whiteout conditions. That photo will probably also tell you why we shouldn't expect to see any direct aircraft-based flux measurements much above the 25 or 6 metres a second we've got in seaplanes, because it would be worse than flying into fog.
I think some people already